Welcome to the mind-blowing world of the kinetic theory of gases. Have you seen a hot air balloon? Are you wondering how that works? How does it get up there and how does it stay there? Well, it's all about the air. And air for sure is made up of matter. That state of matter is what we call gas. And when we learn about these gases, we also learn about the underlying concepts behind it. So let's get started.
To understand this further, let us explore this through a PhET interactive simulation for ideal gases. First thing to do is to add gas particles in the container using the manual pressure pump. Then, we will try to heat the particles by dragging the heat bar upwards. Look at the temperature and pressure. It increases. Now, what happens to the movement of the particles inside the chamber as the temperature and pressure increase? It moves in a faster rate. For another scenario, we will try to cool the particles by dragging the bar in the heat source downwards. Look at the temperature and pressure. It decreases. Now, what happens to the movement of the particles inside the chamber as the temperature and pressure drop? It moves in a slower rate. The other thing we can do is we can change the pressure by adjusting the volume of the container. But remember, we will do this at constant temperature. Pressure right now with our particles in here at 205 Kelvin is 8.4 atmospheric pressure. But if I adjust the volume and make it smaller, what happens with the pressure? It increases. You can notice that same temperature, same amount of particles have a lot more pressure. Meaning, they are gonna have way more collisions as I start to condense them into a smaller space, which is what you would expect because they are gonna collide more, they are gonna hit the walls more, and they are gonna hit each other more. With the help of this gas properties PhET simulation, you are able to visualize how those several macroscopic properties relate with each other. But let us study further.
Firstly, let us ask why you need to study the kinetic molecular theory of gases. Well, it is because with the help of this theory, we can understand the behavior of gases, such as the pressure, volume, temperature, and the relationship between them. For example, kinetic molecular theory of gases explains the inflation of a balloon. When you blow air into a balloon, you are adding more gas molecules into it. As a result, the gas molecules collide with the inner surface of the balloon, and they exert pressure on it, and this pressure causes the balloon to expand. This inflation of a balloon is explained by the kinetic theory of gases. We have learned about different laws that can be applied to ideal gases. Like any laws, these ideal gas laws are merely summaries of observations, such as the way pressure and volume are inversely proportional, or the way volume and temperature are directly proportional. We observe these relationships to always be true. But again, just like any other law, it does not explain why. For that, we are going to need a powerful tool. We need a theory. And the theory that explains the behavior of gases is what we call the kinetic theory of gases. This theory consists of 5 postulates, and from them all, the ideal gas laws can be derived. Let us go through each postulate and talk about what they mean. We make the assumption that a gas is made up of particles, whether they are individual atoms or small molecules, and that these particles are always in motion. Throughout their motion, these particles travel in a straight line unless they collide with something, whether that is another gas particle or the walls of whatever container they are in, at which point they will bounce off and change directions. This vision of gas particles as moving around like billiard balls on a pool table seems pretty intuitive, but it is an important one, as it implies that tiny particles like atoms are subject to laws of motion just like the macroscopic objects are, and that they won't just stop in their tracks and change direction without a cause. We can assume that under most sets of conditions, gas is mostly empty space. This means that the fraction of the total volume that is occupied by the particles of gas themselves is close to zero. That we simply ignore it, regarding them as essentially dimensionless points. This is in stark contrast with solids and liquids, which are non-compressible, because all the particles are pretty much right up against one another. There is a very little empty space between the particles. The phenomenon we refer to as pressure is actually the gas particles in the sample imparting some of their kinetic energy of motion onto the walls of a container every time they collide with it. Just like a macroscopic object would transfer energy onto some surface during a collision. If there are a lot of particles moving very fast, there are many collisions, so the system has a lot of pressure. If there are very few particles moving very slow, therefore the pressure is also slow. We ignore the possibility that gas particles could exert any kind of gravitational or electromagnetic influence on one another. Although they technically can interact slightly due to dispersion interactions or even dipole-dipole interactions if the molecules are polar, we consider such interactions to be entirely negligible. So any collision will be purely elastic or occurring with no loss of kinetic energy. They will simply bounce off of one another once again like balls on a pool table. The average kinetic energy of the particles in the gas is proportional to the temperature in Kelvin. This means that if you increase the temperature, you increase the average kinetic energy, which means the particles will be moving faster. This also means that in the specific context, temperature is entirely indicative of the kinetic molecular velocity. So those are in the 5 postulates of the kinetic molecular theory. These postulates are powerful in explaining the behavior of gases. And to see how, let's quickly review or understand some of the ideal gas laws. For Boyle's law, we can see that if we keep temperature constant, meaning the molecules will move at the same speed. However, increasing the volume must decrease the pressure because the particles have to move farther to reach the sides. And decreasing the volume must then increase the pressure. This is why pressure and volume are inversely proportional. For Charles' law, if we increase the temperature in order to keep the pressure constant, meaning the frequency of collision stays the same, the volume must expand. This is because if the particles move faster but also move farther, they will hit sides with the same frequency as before. This is why volume and temperature are directly proportional. All of these laws, which are simply statements of observation, now make perfect sense in the context of the kinetic molecular theory of gases.